Hi everyone, welcome to Mathemly. Welcome back to our neural networks series. In the last video, we saw how backpropagation allows a network to learn by sending error signals backwards and adjusting weights step by step. But here's something important. Even though backpropagation is powerful, it doesn't always work smoothly. Sometimes the learning signals become too small and learning almost stops. Other times they become too large, causing learning to become unstable or even break completely. These two problems are known as vanishing gradients and exploding gradients. In this video, we will understand what these problems are, why they happen, and why they make training deep neural networks so challenging. Before we look at the problems, let's talk about the goal. Why do we want deep neural networks anyway? The deeper a network is, the more complex the patterns it can recognize. Think of it like a hierarchy. The first layers see simple edges, the middle layers see shapes, and the deepest layers see faces or objects. To solve world-changing problems like self-driving cars or medical diagnosis, we need depth. But depth comes with a cost. The deeper the network, the further the learning signal has to travel, and that is where things go wrong. To understand these problems, we need to recall what a gradient is. During backpropagation, each weight receives a gradient, a signal that tells it how much and in which direction it should change or reduce the loss. You can think of the gradient as a learning instruction. A large gradient means change this weight a lot. A small gradient means change this weight only a little. Gradients flow backwards from the output layer towards the input layer, passing through every neuron along the way. And this is exactly where the problems can begin. Let's start with the vanishing gradient problem. As gradients move backwards through many layers, they are repeatedly multiplied by values related to the network's weights and activation functions. If those values are small, especially when using activations like Sigmoid or Tanh, the gradients shrink at every step. By the time they reach the early layers, the gradients can become almost zero. When that happens, those early layers barely update at all, they stop learning. In our house price model, which predicts $280,000 instead of the actual $300,000, the layers near the output might learn how the price depends on high-level patterns. But the early layers that process raw inputs like size or location barely update at all. These early layers stop learning even though they are crucial for understanding the data. So the network appears to be training, but only part of it is actually improving. Now let's look at the opposite problem, exploding gradients. Here, instead of shrinking, gradients grow larger and larger as they move backwards through the network. This usually happens when weights are large or when many layers amplify the gradient at each step. As a result, weight updates become extremely large, the model's parameters jump wildly, and training becomes unstable or breaks completely. You might see the loss suddenly spike or turn into NaN, not a number, values. In our house price example, this could mean one small error causes massive weight updates. The predicted price suddenly jumps from $280,000 to $900,000, and the loss explodes instead of shrinking. When this happens, training becomes unstable. Weights swing wildly, predictions become erratic, and network fails to converge. Instead of learning gradually, the model overreacts to every mistake. Think of learning like adjusting the volume on a speaker. Vanishing gradients are like turning the knob so gently that the sound barely changes. No matter how long you try, nothing improves. Exploding gradients are the opposite. One tiny adjustment suddenly blasts the volume to the maximum. What we really want is smooth, controlled adjustments, small but meaningful changes that improve the sound step by step. Neural networks face the same challenge when adjusting weights during training. These gradient problems are one of the main reasons why training deep neural networks used to be so difficult. As networks get deeper, gradients must travel through more layers, and the risk of a gradient vanishing or exploding increases. This explains why early neural networks struggled to scale and why deeper models didn't always perform better. They also explain why modern deep learning relies on smarter design choices, such as better activation functions, careful weight initialization, normalization techniques, and improved optimization strategies. All of these were developed to keep gradients stable as they move through many layers. Understanding these issues is crucial because many modern techniques in deep learning were designed specifically to solve them. To sum up, gradients are the signals that drive learning during backpropagation. When gradients become too small, learning slows down or stops. This is the vanishing gradient problem. When gradients become too large, learning becomes unstable. This is the exploding gradient problem. Both issues make training deep neural networks challenging, but they also pave the way for smarter solutions. In the next video, we will move beyond static data and explore networks designed for sequences like text and time-based data. We will introduce recurrent neural networks or RNNs and see how LSTMs or long short-term memory were developed specifically to address problems like vanishing gradients when learning from long sequences. If you found this video helpful, don't forget to like, share and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.